Okay. Okay. Thanks everybody for attending this edition of DVClub. It's a pleasure to have all of you here. We haven't seen such a big turnout before, so it's really heartening to see such a good turnout for DVClub. This is the fourth edition of DVClub that we have hosted in the past 10 months. We have had DVClubs on different topics. The first topic was formal verification, which we had in around September timeframe last year. We had one on UVM subsequently, and we had one DVClub in performance modeling in November last year. So this is the first DVClub edition in 2015, and I believe many of you will find the topics that we are going to discuss today very interesting. Our final presenter for today is Christdas. Christdas is a senior engineer at Test and Verification Singapore. He has worked extensively on SoC verification, and the topic that he is presenting today is co-verification for complex SoC designs. I'll hand it over to Christdas.
Just keep it like this. Okay. So, a very good afternoon to each one of you. It's already past 12, so we changed the time. Okay, so I'm Christdas. I'm working as a senior engineer in Test and Verification Solutions in Singapore. Basically, working as consultant to some of our clients for SoC verification, and been in the VLSI industry for quite some time now. Okay. So, giving you a heads up on my topic right today, co-verification for complex SoC design. First of all, I'd like to make it to you like what are the things I will cover and what I will not cover. So let's have the clear mindset. First of all, here my focus is on SoC verification, and I'm trying to plug in co-verification as one tool which could be effective for SoC verification. So I'm not an expert in co-verification. My main theme is SoC verification, and I would like to highlight how we have identified few areas of SoC verification which would be benefited by co-verification. So that is the agenda for my discussion. Okay, so going ahead. So this doesn't work. Okay. So giving a brief introduction about me, I have around 9 years of experience in front-end verification. I have done a little bit of PD also in the beginning of my career. And I have academic experience also, so I have this more of teaching kind of ask and answer kind of approach to my discussions. And previously I worked with companies like Wipro, Intel, and IBM. I have done a bit of processor verification as well. And I'm a BE in Electronics and Communication, and MTech in Digital Communication from RVC Bangalore. And I'm currently enrolled for a PhD program under the Visvesvaraya Technology University, Karnataka, and going through the coursework examinations. So currently I'm put up in Singapore from around last 1.5 years, supporting our clients in Singapore for SoC verification. Some of our clients have made a classification of their verification efforts into different regions across the world. So Singapore is one hub for SoC verification. So we are a couple of 3 to 4 people set up there from TVS helping those people. This is a bit about me. The presentation is short, so don't worry. I will make sure you eat your lunch in time. Okay. So how I will go about this? First of all, I want to ensure and prove to you people that SoC verification has become complex, or in general, the SoCs have become more complex compared to just 1 decade ago. 1 decade ago, the scenario for SoC was very different as of what we are comparing it to now. So I would like to first show to you that there is a complexity involved in SoC design and verification. The second thing is, how is this complexity demanding new approaches of verification? We cannot run on the traditional horse. It is no more. It will. If there are 10 ways to reach a place, all roads will reach there. But we have to find out which is the quickest way we can reach there, and which is the more efficient way we can reach there. So there are all these old traditional approaches, so-called the well-tested approaches, but now we have to go through and take some bold steps to deviate from them and take up something. So I'm going to talk something about that as well. Then I come into the picture of, even before coming to motivation for co-verification, I would like to portray before you 3 very important challenges we have been facing in SoC verification and how co-verification will fit in there. So I'm not going to extensively go to every aspect of SoC verification, it is too huge, but I will take 3 fundamental things which are latest and which are emerging, and I would like to kind of connect co-verification with them, and then we'll have a look at the advantages and summary. It's going to be very crisp and short. Okay. So feel free to stop me if you have any doubts. It will be a mutual learning. If I don't know, I will ask you. If I know, I will answer, or we can take it offline, or we can come up with something. Okay. Basically, adding just this one slide about TVS, though it is supposed to be only on co-verification, but wanted to put this one slide about TVS because we are here showing that we are highlighting in TVS on these 4 aspects: verification services, verification IP, verification training, and verification productivity tools. Okay. Why I'm showing this slide? Because this is one important area which I want to highlight. Verification productivity. Verification productivity is something which is not being addressed by all consulting companies, but at TVS we are giving importance to that. So that's why we jump into. So you may say, you being a consultant in a company, you go there, you are meant to implement and you just have to execute and make sure they tape out in time. But we step ahead and say, we think that this methodology can be changed for a better improvement, or we can do things better like this, and we propose few things. So that is being encouraged at TVS. That's what I just wanted to highlight here. Okay, not spending much time on this slide. So coming to the complexity of SoC verification. Just a few years ago, if you can talk about SoC verification, it was something like they say, oh, we have all the pre-verified IPs, it's just a matter of integration. You know. Then they say, oh, okay, have you reached the toggle coverage? Then it's done. Yeah. Then all the way functionality has been checked and things like that. Because the design needs to be a bit simple compared to what is being used now. You like it or don't like it, the number of cores in the SoC are being doubled every year. The last design we worked on had only 2 cores. Now this year we are working on 6 cores with redundancy, with comparators to make sure if 1 core fails, we have 1 more core in the backup. So the complexity is kind of increasing. So in general, right, I wanted to highlight few things which will add to the complexity of the SoC verification here. First of all, it's multi-core, so the number of cores are increasing. Then we have low power. Low power is taking a big role here. No, even for my PhD topic, everyone suggests me to take low power. No, everyone wants to get into low power. They want minimum battery size and more power from it. So we have islands, and we have to do the power verification, making sure that they are going into standby, coming out efficiently, and there is no issue when somebody is talking to each other. Make sure that both are active and things like that. So low power is taking an important aspect in SoC verification. And we have multiple clock domain crossing problems are there, and we have multiple boot options. Customer have a never-ending list of what they want from us. Somebody wants from flash, somebody wants from boot ROM, somebody wants more SRAM and things like that. And we have complex bus protocols. Some of our clients are using their own specific bus protocols. I don't know if I'm not allowed to name the clients, but it is not like it is always the ARM-based generalized bus is used everywhere. There are different processes being used and different set of bus verification, bus protocols being used. So it is not kind of the market is having few solutions for something, we can just take it and plug it in. Not possible, because every client has its own unique bus. Sometimes they are using the unique bus protocol. And we have the DFT and debug support. This is also very important these days. We have seen, I have worked on SoCs which will change in cost around 10 times just because one SoC supports debug support. You may be surprised by this, but that's true. We have a basic design of SoC. The same SoC with debug support will cost 10 times more to the customer, but there are customers ready to buy that because debug has become a crucial thing for them. So we sell different versions of SoCs, like one with debug, one without debug. We have emulation devices, we have product devices and things like that. Okay, so we have firmware, which is kind of coming into picture now and then, and it is also getting complex. We are putting more and more things into the firmware. So overall, I just want to convince you that SoC verification or SoC design is now complex. I hope you all agree with this. So with this background, now let's see how this impacts our verification. Okay, SoC verification is not just about functional verification anymore. Look at the scope it has. So many aspects are to be covered. Every small detail, one small detail added to SoC as an enhancement feature adds 4 verification tasks. At least 4 verification tasks. So every time the designer feels like, oh, I want to add something more, then the verification engineer has to realize that he has to do 4 new tasks for him. So that's how the complexity of verification is also increasing here. Apart from the traditional connectivity check which we used to do, now we have something like we are doing the debug support, we are having DFT, we are having checking on the pads, we have analog and digital mixed parts and how we handle that, and we also take care of system states. Okay, what is the significance of system states? I want to give a short talk on that as well actually. Most of the times we have seen that the applications in which our SoCs are being used, especially the automobile industry, are dependent on the phases through which the SoC goes through. Let us say, for example, we have a anti-braking system. That's one of the important SoCs developed by one of our clients, anti-braking system or something like that. So it is crucial that what are the series of events that happened before the brake was applied. So it is kind of a specific scenario, like was the throttle high or was the EVR able to handle the voltage which was given to it and things like that, and why did the brake fail at that point in time, something like that. So system states also plays a crucial role, meaning to say transitioning the SoC or the overall system from different states of operation. This is more of a system level verification though, but it is important, it has to be checked. So overall, I wanted to show to you and prove to you that there is a higher scope for verification as long as the complex SoCs are concerned. Okay. Now moving to the next slide. Okay, this is the summary out of the previous 2 slides. Modern SoCs have become so complex that simulation alone cannot verify enough of design state space. We must use multiple verification strategies in concert to achieve the goal. The new approach would involve an hybrid verification environment comprising of RTL simulation, gate level simulation, formal verification, and emulation. So we have multiple players coming in now. The legacy RTL simulation, apart from that, we have now emulation coming in. We have formal coming in, formal taking an important role, and we have gate level simulation and all these things. Now, the next challenging question would be what to do with what? Meaning to say, we have a huge piece of verification space. Which one to be handled with what? Which one to what percentage? Can I do everything with formal? Some people, I can do everything with formal, but it may not be the efficient way. How much percentage of verification will go into formal? How much can be handled by traditional RTL simulation? Is GLS still required? And how about emulation? All these things we have to evaluate, and that is we have concept engineers who have very high experience who kind of evaluate these things and decide the methodology. So slowly with experience we move to the domain and understanding where we can say, okay, this is needed, this is not needed. In one of our clients, they don't do GLS. How many of you are aware of what is use case verification? Use case verification? Can I see if anybody is aware of use case verification? No, I know this is a classroom approach. I have been a lecturer before, so I'm just. Anybody knows what is use case verification? Okay. Use case verification is taking a very important role in SoC verification. It is something like we are mimicking the customer environment even before we give the product to them. We want to make sure that it will not fail in their environment. We take some basic things from them which they can share with us. We understand the frame structure of their software, how it works, and we try to mimic. We try to mimic the behavior of the system, how they will be using. Not just that I can say I verified all the functionalities, 1, 2, 3, tick, tick, done, verification. But in the real scenario, it may not exactly match how the chip has to behave. So use case verification is taking a very important role in SoC verification. What is the problem with use case verification? The simulation runs for at least 2 weeks or something like that. You start something, the scenarios or something like that, it takes the license and keeps running and running and running. So most of the companies are now thinking of prototyping and also thinking about emulation for use case verification. Use case verification, it is so fast, so quick using emulation device. You just put being when we come back and say, oh, we have to respin this, then at least, a lot of effort goes into ECOs and a set of respin things. And then they say, usually they say, oh, you're doing a respin. I want to add one more feature into that, yeah? Then they come and put one more feature into that. And if that goes bad, then, one more cycle, things will happen. Anyway, so use case verification actually helps us to identify system level integration issues in the very much beginning. And we can also mimic the hardware-software interactions. Hardware-software interaction. Nowadays, a pure electronics company, meaning to say who is into the design and the verification of maybe say SoC or ASIC or something, are stepping ahead and saying we will provide some drivers to you folks, to the customer. The drivers which they can use it for their own environment and they can give it to the customers on which they can build their software. We call them low-level drivers actually. So that approach has started, so that we have a common environment at least at the lower level, and we can kind of test things equivalently. They can also use the same drivers and they can build their software, and we can use the same drivers on our hardware and check that things are working fine. So hardware-software interactions are also being taken care in use case verification. System level corner cases can be checked. This is understood. Customer concerns efficiently addressed. Every time we give out a product, when we come back, there will be a list of complaints from the customer that we want more on this, we want more safety on this, we want this to be password protected, we don't want this block to access this block, all those things. When there are multiple layers, we give to one person, and he has one more software vendor, and all those things are there. So customer concerns can be efficiently, tested even before we are saying that this is the final product we are giving to. So this is use case verification. Yeah, this is the safety verification what I was talking about. So the key word here is the takeaway word is ISO 26262. If somebody puts on their LinkedIn profile as a safety verification expert, now next time you should know that this is related to ISO 26262. It is safety compliant European agency which is set up rule. It is not just about few points there, it is about the methodology which we are using. They have a stringent methodology. Are you doing this? Are you doing this? Are you doing this at different levels of time? And they do the audits and then they give the complaints. Customer assumptions verified. This is one important point I wanted to highlight here. Sometimes we say we expect the customer to use it like this. The ball is out of our court now. We just said it and pass it on. But they are saying when you're claiming that, have you verified that when customer uses it like that, does it really work? So this is called customer assumptions being verified. So anytime we have a customer assumption on the spec, the ISO 262 comes and says, show us a test case which is verifying this. Then we have to show that test case. So customer assumptions are to be verified. And reliability testing and error injection. This is taking an important role. There's something called RAS. It is actually a software topic basically. Reliability, availability, and service availability. This is very dominant in mainframes and servers and things like that, where we challenge zero downtime and server will run for hundreds of years without boot up and things like that. Such scenario we thought would only restrict it to processors and servers, but SoC also in some terms needs this error injection scenarios and correction. So we usually go for this EDC codes, error correction codes, and every bus has to have some ECC bits along coming with that for protection to make sure that there is no error. And if there is error, how many bit of error can be corrected? So this is kind of negative verification. We inject error purposely and we see how it propagates. And we have dedicated blocks in the SoC which will kind of highlight that there was an error and they go for correction. Okay. So basically we are looking for fail-proof systems. Yeah. Okay. When we talk about, go ahead, sorry. Mm-hmm. Oh, okay. We have something called stacked faults. We have something called socket faults. Like let's say a bus, one of the bus bit is tied to high. We don't know. It's always high, so we don't know. So that could be one error.
Those things anyway will verify primary job is finding those things. But if something goes wrong in the fab, something got stuck, anyway we are doing it in the tester on socket version stuff parts. So if within the chip, they may not be required.
No, actually it is not just about socket faults. If let's say there's an issue with the flash, let's say that some memory is getting corrupted by itself. So we have to have ECC checks on every flash location. We have to have dedicated ECC bits coming out. Only then we can find out. Otherwise, therefore, we intentionally do a bit flip and try to create such scenario and check that. So this is kind of a negative verification on that, and we have to give some fit trace to them saying that this is tolerant to this much fault level, and we have some numbers to get it from there. Okay. Okay, so in error.
So possibly you are introducing a CDC failure scenario, or what kind of errors?
Okay, basically, right. Protocol failure is in general functional issue, so the test would fail. It is not like it should be a special test case for that to verify. You give and send a signal and the act doesn't come up, it fails. So here, when I'm telling error injection scenarios, we have many categories. Like we have something called targeted error injection. Targeted error injection meaning, let us say there is a flop. What happens if the output of that flop is kind of changed, or it is getting negated or something like that? It's like targeted meaning it is like a corner case. This is one place which is crucial, and you inject specifically there. Okay. Then we have another thing, something called random error injection. Random error injection, you randomly flip some bit in the system, randomly flip, and we have these random generators where some bit will be randomly picked, and now the test case goes on. Will it be really caught down the line? This is random injection, and most of the time there is called something called error edge injection. Error edge injection basically for memories. Initially the built-in self-tests are run, and are we able to catch if there is any issues and things like that. So there are different classifications within that. So there's usually not in every SoC company, but in the processor companies we have something called RAS teams. It's called reliability, availability, serviceability teams, who will do this error injection scenarios. Correct. So the sleep modes and all, right, when you're going and coming out, so sometimes that can be, that's where the bugs hide. So manager always says the bug is hiding this. Okay.
And do we really get the time to do this?
You know what, this is a very interesting question. I would like to answer this. We always think like that should we really do this? Yeah, come on, it's okay. But now it has become mandatory because we want to take the complaints. Yeah. People know how to make somebody work, okay. So they said, unless you don't show us this, then we are not going to give complaints. Then if it is not complaint, customers won't buy. It is like a standard. It is like, ISI in India or something like that, right? You have ISI mark, you sell it. So,
December marketing products. You really need that is the most response are going. If you say automobile industry, yes. How many automobiles are built per year for 10 years? But every year I'm built here for mobile phones.
Yeah, it all depends, right? You want to keep up your brand name, you want to have always that the so-called best guy on the market, then you have to, there's no other go. You have to somehow plan, take resources and do it.
I think that's a big topic. You want to have more resources, or you want to run more tests, something was there. One book was there, verification by system level,
Crispy, yeah.
And the introduction of your last, probably 50 close the project.
So Crispy also says, if things can go bad, they will. So we have to be ready with that as well. Anyway, let's move on. We are running out of time anyway. Okay. So system level verification, I don't want to spend much time here. You all know about it. So stress testing is done. Okay, hardware software deadlocks. This is important. Okay, this is not taught at any level except at the system level. Hardware software deadlocks. Let us say so important. You want a product we efficiently tested only at the system level. Okay. No, we are not creating. No, we are not creating a deadlock scenario as such. We are not creating a deadlock scenario as such, but because we have 6 cores, it's kind of a multi-threaded approach. So we want to see whether will that create a problem, especially when we have in between giving some resets. In the middle of the course, you want to give some application reset or something like that, then things will change. Some assumptions which you have not made comes up there.
These things also go as our verification test case, but really impossible to figure out that class will happen.
Yeah.
When I attend the test case,
system level verification test cases are usually more of having the software content, and they are more kind of use case only, how the customer will use it and things like that. So we hope that things will go fine in that. But I don't see any negative testing being done. That's what I was trying to convey. Negative testing, no, at that level. Meaning to say purposely create a scenario for a deadlock and see will it come. No, if deadlock is created, it will die. That's all. There is no way of it coming out. I don't know. Maybe. There may be ways out of it, but at least I'm not aware. Okay, so we have to run through the slides, very few slides. This, I think. So the basic fundamental idea, as you all know, is that we wait for the first silicon to come up, and once we have the first silicon, we run our software. So okay, we are ready. So we run and we get surprises. Then the cycle starts of clearing up and things. So the co-verification idea was that even before, okay, this is interesting. Huh? Some people said that let us do co-verification when the RTL is frozen. But some people claim that it is better to do co-verification even before the RTL is frozen, because we have scope for making modification to RTL. If we find something, we still have the scope to make modification in RTL and still have the fix in hardware rather than making a software patch. So if it is frozen, we are giving you, we are doing the PD of it, but we cannot change anything. Then it will go as a ECU and things like that. So everyone says, when I feel that next month my hardware is going to get frozen, my RTL is getting, it's better I deliver it now and say, okay guys, software guys, you can start working on it. And if they come up with something, I can twist and make changes here. Okay. So that is the concept of co-verification here. Software development and debug performed on FreezeRTL till almost FreezeR. That's why I put almost there, rather than on the first silicon. Efficient reduction in time to market, delay of the product, scope to fix system level bugs in hardware rather than a software patch. I spoke about it. Risk spins efficiently avoided. System performance measured at very early design stage. Okay, this is also important. System performance is measured at early design stage because of co-verification. Okay. This is what I wanted to tell. That's why all this background now. Co-verification is helpful for application use case verification. This is my main point which I wanted to give out. This is my takeaway. This is what we have identified and this is what we are proposing. If you want to have an efficient application verification or use case verification, co-verification is helpful there. The second thing is co-verification can be helpful for system stress testing. Instead of running in simulations for long hours, just go for a prototyping of that or put it in an emulation and make it faster and stress the device as much as possible. So that is kind of anything which is supporting emulation is kind of helpful in co-verification as well. That is the bottom line. Emulation supports co-verification and has got good EDA support. This is a plus point. This is a plus point. Because we already have EDA support for emulation, the same horse can drive co-verification also. We don't need to rebuild something. Use the same emulation setup and plug in your software which you are developing. Market delays. System testing and complete software debugging environment. This is the conclusion and this is the summary. Software content of electronic products is increasing exponentially and is most often facing item for product completion. Software simulation alone is not fast enough to test the volume of the software being written for today's electronic products. Using acceleration and emulation for hardware software cooperation takes advantage of the investment made in emulator for SoC verification to speed software debugging, thus shortening product cycles by several months. So I think this is the last slide, hopefully. Yeah. Okay. So here, I would like to, on a lighter note, whenever we have a crisis, consultants are always called in the time of crisis. So they say, oh, there's only 1 month left. Let's call the consultants. So we always go for firefighting. And there's an interesting statement I always hear. They say, we want it fast. That's the first thing the managers say. We want it fast. We want it good. Want it fast and want it good. They want both. So always there is a compromise there. If you want it really fast, then you have to give more time. If you want it really good, you want to give more time. If you want it really fast, you have to compromise here and there. So, but emulation, right, is kind of helpful in both ways. If you see, it is faster. At the same time, it is good also, but it is costing. There is money involved in that. So there's always a trade-off between every approach we take. But it all depends like what is best for us and what we can take and things like that. Okay. So this was my talk and I'm so glad that I'm here today. And if you have any doubts, you can ask me now. If I know the answer, I tell, otherwise I get back to you. Or you can correct. Mm. Hmm.
So, is there for FPGA prototyping
Okay. Mm-hmm.
Is there any other response, other software codification before that stage?
So either it can be, if you say if it's FPGA, it is. Now the problem with FPGA is, right, do we have FPGAs which can contain the big designs? That's a challenging thing actually. At least I know one case where we were trying to do. Okay, I think I can tell the name. It's called Power 7 PC, right? It's from IBM. So we were trying for. They were trying for something called emulation-based verification approach. But the problem was the FPGAs couldn't handle that huge design size. So that was a problem at one point in time. We saw that. So FPGA is okay for small designs, I believe, but not for the huge one. But I think they have something called Palladium or something like that, right? Sorry?
I saw one of the customers having 32 big vertex FPGAs
in
the single board.
Okay.
Using single FPGA, it has gone. Now we are partitioning our design to multiple FPGAs, putting different FPGAs. We are in the partition. And ARM also we are started using the versatile boards. There is ARM processing separately, and you have separate 2 or 3 FPGAs available. You can partition your design and put it to different FPGAs and verify. So any big chip, for example, I have 6 multi-cores and 200 IPs. That means I can go and put into my generalized FPGA board.
But the idea is right, we should not spend too much of effort making it work. Rather than say, like, if you have this distributed system of multiple FPGAs, then you have to break your design also, that where you want to put where and things like that. So,
everything to the tool is not extend.
You
have to go really
performance testing also, we can use FPGAs for that. That is easier way actually. But I think there are a lot of PDA companies which have come up with solutions which they have a software debug environment at the same time. They have the FPGA kits which will help. Right? I think I'm at least aware of one Altera kit, something like that. Neo Cyclone or something like that was there, which we used to use long ago. I don't know now if it is available or something. They have a integrated debug environment which can be used on a PC or something, and they also have the complete system like it. You have to just port your design and do the stress testing and check things like that. Data-based interfaces are there, which we can use. It's also there. I have also seen cases where they don't put everything as RTL. Sometimes they put IS as a simulator model, or for the processor they put the model, and for the other thing they put RTL, and they make combination of which is crucial part. They have a system C model of that or something like that, and the other thing they put RTL. So this approach also sometimes helps if the design is huge. So something like that. So I'm not really sure of many options as such as you asked the question, but I know few of things. Now we have proposed this for one of our clients for use case verification. So we have to see if we involve in that, then we get to know how, if the system is huge. So we have to see how it goes. Okay, I think we have run out of time. Shyam, thanks for pulling me into this. Thanks, Nazneen, and we'll see how things go. Thank you so much.
Thank you, Christdas, again. For the next SoC verification. So DVClub events to each of you so that you can keep updated and decide which ones to participate in. Thank you all for coming. It has been a pleasure having you. Lunch is outside. Please have a good time. Thank you.